Thank you.
Marissa, do you have intel of the take-home quiz and the homework, or is it all?
Oh, I have this. I forgot to get the homework. I can grab that too.
Okay. I got a lot of stuff to get here. She understands. I haven't even really started the business stuff this week. Yeah. Yeah. Have you started using homework questions?
For this week, I tried.
I tried.
And then I was like,
I tried T4 once, and I was like, I literally don't even understand the start of this already. And then I just moved on to like one of these AI questions and was actually able to do that. I've only done one.
After the class activities, I think I can probably go back and do it because like we kind of sort it out a bit more. But I know, right? Of course, that was the goal.
Oh, it's so hard to get appointments that when she was like, oh, I have an opening on this day. When she was like, out. And she was like, oh, I have an opening for next week. And I'm like, yes, yes.
Yep. I had to take a dentist appointment like a couple weeks ago, and it was during, it might have been during business week. It was during one of my classes. Yeah, right?
The week after next presentations, right?
Yeah. Ready?
I still need to wrap up.
Oh, I think I forgot to print out the homework. That's what I forgot to do.
I can print that out.
Okay.
Do you want the lab?
Sure, I'll take it.
I know you don't do due dates, so
Yeah.
any time you can get ahead, I try.
Yeah.
You know, all this time is all this first part is all gonna be easy.
Thank you.
Yeah, no, stapling that over there.
Yeah.
I'm gonna have to leave a little before 12:50 because I have an online class I have to get home for. That starts at 1. I live like 20 minutes away.
Okay.
Okay.
Are you looking for the homework or something?
Yeah.
I'll print it out at the break. I forgot it.
Okay.
All right, let's get started since we have a lot to try to cover. And so the first part of lecture is kind of like fun facts and just like random equations type of thing. And so I know this starts to get just kind of hodgepodgey. And so right now we just want to appreciate that these metals can do all sorts of things, so they can act as centers for these ligands. And so I just wanted to kind of demonstrate that and how it works. So we have just a scandium 3 chloride, so pretty standard, and then we're going to kind of see how scandium acts as basically just a D3. And so we can kind of simplify that. That's why it makes our scandium 3 chloride. And then we can see that we can add it to ligands. So the CP star is commonly used. So this is this thing, CP star, and then you can make the salt of CP star lithium. So then you can add it to metals, and you can see right your product. So you'd be forming lithium chloride as your byproduct. You can filter off that salt, and then you'd be left with your complex. And then so kind of the idea is you want these metals to do cool things so that you get research funding. And so some of those cool things would be like adding N2 across. So maybe you can make ammonia eventually, so that'd be kind of the goal. So that's kind of shown here, addition of the nitrogen across. And then you kind of got a mini taste of this in your one-pot reactions. But then kind of, you know, what we as chemists do, and this is all like organometallic chemistry, is that then you try to reduce it or oxidize it, right? Change the oxidation state, see if it does other cool stuff, basically. And so there, they use potassium a lot as a reductant, so we see that. And all these reactions, these that I'm showing are going to be like air-free, really sensitive conditions, so that's why they got to use potassium metal, that sort of thing. So again, just kind of appreciate it, take it in. Like, okay, they do cool stuff, so right, adding carbons to this nitrogen, so if they could release that product, that'd be kind of the ideal. And so then we move to titanium. So again, just kind of taking a tour of our D block now and our metals, so kind of refamiliarizing ourselves. And does anybody remember titanium dioxide? It came out in the news relatively recently. No random trivia. Okay, so titanium dioxide, it has a variety of uses. So sometimes it can be used as sunscreen, and so titanium dioxide is basically a white powder, and so it's a good physical sunscreen. I've also seen it used in like water purification, so it can act as kind of like a coagulant. Yeah.
The sunscreen, is it because like the particles are getting in the way of the...
Yeah, so it's a really effective barrier, exactly, because it's like a physical. So I think zinc oxide is also similar. So yeah, there's like white metal oxides that just reflect the sun right back. So yeah, it's just that physical barrier. But then what I was alluding to is there's like this whole, I'm not sure how much of it was sensationalized, but they were talking about titanium dioxide and Skittles, if you remember. And that was a big thing. And they were saying, oh, it's so toxic, which I was questioning how toxic it is, because I know they also use titanium dioxide as like in food products as whiteners. So like, I don't know if you've ever eaten vegan cream cheese, but it has titanium dioxide in there to make it white. So used for food. So yeah, I'm not sure if it's carcinogenic, right? They always come out with a new study that everything's carcinogenic, so who knows? All I know is that was recently in the news about Skittles and titanium dioxide, but I haven't dived into the literature. And other fun facts about titanium dioxide. So it could also be used in times of war. So we mentioned that, right? It's like a nice white product. And again, chemists always have a messed up sense of humor. So we call this tickle. I don't know why it reacts instantly with the water. So what it does, and you can look at videos of this, you could also do silicon dioxide or silicon tetrachloride. But again, in times of war, you have this nasty chemical, titanium tetrachloride, or it could be silicon tetrachloride. You dump it out of the plane, it reacts with the water in the air, creates a smoke screen of chaos, so now they can't see, and then also poisons them with hydrochloric acid. So not good. So you can see why it's used for that. All right, so moving on. So now we're kind of going across here. So now we're looking at vanadium. And so vanadium's kind of cool. Your book mentions that vanadium is amphoteric. So remember that it could be an acid or a base. And so it mentions that then, right, this vanadium can form different complexes and pretty colors at different pHs. And then chromium, I didn't show any cool chromium compounds, but your book mentioned it being used as a chromous bubbler, so sometimes this is used to remove traces of oxygen gas, so this would be a good setup use. So sometimes this would be used, right, we mentioned air-free chemistry, and so if you thought that your gas, so right, you get a tank of nitrogen gas or whatever, argon, hook it up to your line, if you think it's impure, then this is where you might use a chromous bubbler. Although usually I'll just give a fun fact. So I've never personally used a chromous bubbler because usually you buy gases that are like UHP grade, it's called, ultra high purity, and it's like 99.999% that gas. And usually that is good and that's fine. But if you were using something, you know, maybe more impure, that's where the bubbler would come into play. But I think nowadays you just try to buy the pure gas if you can afford it. And so manganese, I think we'll look at some more manganese reactions later when we dive back into our organic chemistry chapter, but let's at least kind of talk about what it does. And so manganese is used as an oxidizing agent. And so it can add oxygens to double bonds. So with our alkenes and also alkynes, it can do this sort of transformation. And so it kind of depends what the substituent is. And so either it tends to kind of break this double bond entirely, and then you'd form like your ketone or aldehyde, or sometimes it just adds the alcohol across, depending on the conditions. And so, again, just kind of briefly, so condition dependent. And so the key takeaway is we want to say, okay, well, we know that our permanganate reacts with our double bonds. And so again, we'll cover it again, but it's a good kind of preview to everything. So I'll keep it moving. So iron is pretty cool. So iron is used in a lot of different chemistries, so it has some relevance. So there's a lot of different iron compounds, so I chose these since these are pretty cool, a family. And then this becomes a theme in chemistry as well. You have what's called this tripodal ligand or tetradentate ligand, so depending how you want to define it, but you kind of have this, it's called tripodal since it kind of looks like a little stool with 3 legs, and it's a very stable type of structure here. And then you have these 3 phosphines acting as ligands. So that's something to kind of appreciate. So we're kind of learning what can act as ligands, right? We've seen ammonia, and again, a ligand is just something that attaches, right? So this is a ligand, this is a ligand, right? That's just the fancy name we call whatever's attaching to the metal is our ligand. And right, and as we're seeing, these things can get big, And this is also what I was implying about the naming system, that then in research, everyone starts inventing their own names anyways, so. And some more reactions. And so this is how you can purify iron, make out iron. So in these smelting, so right, you take your impure kind of iron ore that has your iron oxides, and then they keep it in an oxygen-rich environment and add CO and different gases, so then you can get out, right, your molten metals, so then they can isolate iron out. And then, of course, right, other products as well being isolated from our iron ore, and then any other, right, stone mixture. So this is a mixture of iron ore and limestone, so, right, our calcium carbonate. Oh, and let me show another fun compound. So we'll go back to this concept towards the end of lecture, but we'll get into kind of high spin, low spin, what does that mean? And so I just wanted to show you that, right, people care about this, that this is cool in research, that we want to characterize our compounds, and that we have, different techniques. So again, you don't have to know what they are, but just kind of appreciate that they exist. So there's things called EPR. So that's specifically used for looking at like iron, and this data kind of tells you what spin state it's in. And so that's how they get, right, the spin, so 3/2, blah, blah, blah. But, right, basically we're just kind of appreciating people care about this. We can characterize it, and this is how. And then we'll go back to kind of our basics. All right, so that was kind of fun fact hodgepodge. Did I skip something? Oh, I think I skipped page 2. So I skipped cobalt. I know I skipped some stuff. So cobalt, let me show some stuff. So cobalt is also used a lot in different like CO2 reduction complexes. And again, I just kind of want to demonstrate the cool stuff it can do. And this is another theme in chemistry, a bunch of nitrogens acting as ligands. So that's also pretty common, so either nitrogen or phosphorus. Sometimes you see sulfur, but usually those two. And then again, just appreciate, right, we have a metal in a low state, so cobalt 1. So that's usually what you want for like these organometallic reactions. Start with a low metal state, so, cobalt 1 generally, or any like iron 1. And then from there, why you want it to be in a low oxidation state is so then it can add your cool thing. So in this case, right, they're trying to do CO2 and maybe make methanol or something cool with it. And so we just, again, appreciate how this metal then is able to bind that CO2. Notice that it changes oxidation states. And then again, right, in research, you just kind of play with it, right? Try to add an electron, so try to reduce it. What does it do? Does it do something cool? That sort of thing. And so cobalt's also used in a lot of other things. So you might see like cobalt glass, which just has different cobalt oxides, really beautiful, like a dark blue glass thing. And then other variations, so like cobalt phosphate, that gives a lavender pigment. Cobalt sulfate is used in batteries and both ceramics. So again, all these cobalt colors are all pretty. And then it also mentions nickel, so right, nickel compounds can also be used. Well, they only mention nickel plating. And so nickel is also really important, so I just kind of showed again a few reactions. And so nickel tends to do 1 electron or 2 electron transformations. And then we just want to remember too, right, that it is biologically relevant. So this kind of gets into like bioinorganic chemistry too, if you want to take this route. And so that's the other thing, right? A lot of this research is kind of bio-inspired. And so this is looking at the dehydrogenase catalyst. So, right, this is in plants, so reduction of CO2 to CO. And the picture that I was trying to show you guys, right, is we care about kind of this sort of center, and so a lot of research has been done over the years of trying to mimic this. So there's a lot of like iron sulfur compounds that people have tried to study and get to do cool stuff. And so people are trying to understand like why is the nickel there, and you got this sulfur thing, how does it work, how can we mimic it? So that's kind of research. And let's see, so copper we'll look at. So of course, right, the Statue of Liberty is made of copper, and then it's green since that copper has been oxidizing over time. And other things are just kind of appreciating that our hydrates can have different compounds or colors. And so this is copper 2 sulfate, and right, I think we've seen this in class. We get it as a little bottle solution, aqueous, and so it has those 5 waters complex to it, so it's blue. But then if you were to make anhydrous copper sulfate, it would be white. And again, that tells us, right, whether things are attached to it, so it starts to speak to the electronic nature of our element. Let's see, what should we say? So zinc, I guess I didn't have anything too exciting about zinc. Just again, kind of zinc oxide. So it could be used as sunscreens as well. I think this is also used as a mold inhibitor and used in photography development, along with some of those silver compounds. And then zinc, right, usually 2+ oxidation state. So zinc isn't too interesting since it doesn't do multiple oxidation states. And so gold can be cool, and so that's kind of the other trick of organometallic chemistry is things generally get cooler as you move down. So copper, right, might stare at you, and silver sometimes is reactive, but gold, like all these down here, they can do more reaction. So like iridium is used a lot, osmium does some things, and platinum, of course, is nice, gold is nice. Let me pull up. I'll at least pull up one paper with a gold compound. And so this one, I think the copper and silver compounds just kind of stared at the researcher, but then the gold one could do a bunch of stuff electrocatalytically, so that's just some example. So the larger metals tend to be more stable, so again, they can do different transformations and carry those oxidation states better. And so blah, 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 we can look at these other applications of gold. So of course, right, we've seen a lot of different compounds in photography as well in development, and then obviously, right, making pretty things, so different glasses, porcelain, all sorts of coloring. There's the silver oxide again, so used in photography, or silver bromide, so these are photosensitive. And then mercury, so used to kind of be used more, but then of course, right, the toxicity of mercury has made it not favorable. So it used to be a fungicide, but don't really want to be releasing that into the environment. Also used as, again, paints and pigments. I think also used, right, as makeup, and people went insane because of that. Have we seen mercury and sodium reacting? This is kind of fun. Let's at least. Oh, maybe I have to click. Oh, no, that's something else. Come on, full screen. No, unavailable. Oh, now we have an ad.
There There's a way to cut your dishwashing time by 50%. Try Dawn Power Wash Dish Spray. It removes 99% of grease and grime in half the time. It cleans so well, you can replace multiple cleaning products. Try Dawn Power Wash.
I saved
my
hundreds
gosh.
with Liberty Mutual.
All those
Liberty,
ads
liberty,
play.
liberty,
Let's
liberty.
look. I think I've told this story maybe
This video has
before
been sponsored by
in
NordVPN.
class.
You can get a special deal
But
and support the channel
mercury
by visiting
compounds are pretty toxic, like organic
nordvpn.com/NileRad.
mercury compounds. And so this is a sad story
Over the years, I've worked with mercury
of just actually an experienced chemist, and I don't know why she was working with dimethylmercury. I don't know if she was just trying to get a standard or something. But basically, she just had a tiny drop or two of the liquid on her glove. So even though she was wearing a glove, it went straight through and still poisoned her, which is, I mean, horrible. And so she didn't even know, right, that she had been poisoned at the time. And then kind of months later, she started getting ill and then, you know, died. So it mentions, right, blah, blah, blah. Over the next couple of months, she worsened. So just that mercury poisoning had already taken place. And so, you know, she died. I don't know whether she could have been saved, you know, if they had caught it earlier. I mean, they said it was pretty high, so 800 times. So there are like some chelating agents, but it can be difficult to try to remove mercury, because then you have to try to take a substance that mercury will bind to and then get out of your body. And, you know, that can be a process, right, trying to get something to chelate out. So, yeah, that can be difficult to treat. I'm not entirely sure. I don't know if they know, like, the mechanism for this sort of thing. I know it just, like, messes with your brain functions, essentially, and, like, yeah, because you start getting, like, slurred speech and, like, weird motor functions and just total. With the organomercury. So, yeah, it's a lot different from, like, just the regular mercury. So if you had, like, regular mercury, so, like, the liquid mercury, you probably, you know, it's not a good practice to touch it with your bare hands, but you probably could, and you'd probably be fine. It's just the organomercury, because it's in a liquid form, then it just goes like right through you and right through your body. But yeah, that's kind of also why mercury has gotten a really bad reputation from like the organomercury compounds. And especially because the dimethylmercury is really small too, so it can just kind of go. And it might also act as like a methylating agent. And so that means that it could start like methylating random things in your body. So who knows what that would do potentially. So there's a lot of things to consider. All right, let's look at this reaction, hopefully.
many times, and it's almost
I'm gonna
always a
skip
bit of a
ahead
pain
to where they're
because it
actually
requires special
adding it.
handling. So just using a really large flask, but they were also
I
doing
forgot
it
the
on a
point.
much larger scale. I figured that because I was only doing this with a few milliliters of mercury, a large test tube would probably be fine. So I poured in a random small amount of mercury, and then I pulled out my small piece of sodium, quickly dried it, and threw it in.
All right, this is my one criticism of his technique. So I've done this before, but I would always do it the other way. So you put the sodium on bottom, and then you pour the mercury on top, and then it reacts instantly. But he didn't do that, but we'll see. He'll kind of shove it in.
I was kind of nervous that I'd immediately get fire in molten sodium, but nothing happened. The major reason for this seemed to be that the sodium was just a bit too tarnished, and it prevented it from coming into contact with the mercury. The sodium's also way less dense than the mercury, so it kind of just floated on top, which didn't really help either. To fix this, according to some procedures that I read, it's pretty common to use something like a glass rod and to shove the sodium into the mercury. Then once it's underneath, it can be scraped and crushed to expose the fresh sodium. So I decided to try this, and initially I still had some trouble getting it started, but then suddenly there was a little thump, and all the sodium instantly disappeared. Then when I mixed it around a bit, I noticed that the texture of the mercury had also changed. The reason for this was because as the sodium combined with the mercury, it didn't do it uniformly. The reaction was extremely fast, and the mercury that was around the sodium took up most of it and got a relatively high concentration. And when the concentration of sodium gets above about 1% by mass in mercury, it starts to solidify. So what this gave me was a bunch of solid sodium amalgam mixed in with some regular liquid mercury. However, after I let it sit there for a few minutes, the sodium slowly dispersed evenly throughout the mercury and most of the solid bits disappeared. It kind of went back to more or less looking like regular mercury.
All right, so I'll stop it there. So that's just to show you one of two things. So, right, you can see that mercury tends to react with metals. So maybe you've seen that in other videos where they like destroy, airplanes and stuff with a little bit of mercury, since it starts reacting with the metal and can absorb other metals. Why we want to look at sodium, and he kind of mentioned, right, this keeping it around 1% sodium amalgam. So this is a common practice in organometallic chemistry sometimes. So sometimes you don't want to just hit it with the pure sodium, right? It's too much and it's not going to work well with your compound. But if you make this sodium amalgam and then kind of pour your reaction over the sodium amalgam, now it's just a 1% and it can react a lot more slowly and kind of more controlled. So that can kind of help. And I'll also put on there, so there's a substance called KC8. And so it's literally just like you heat the shit out of potassium in the presence of carbon, and then it makes a really pretty gold compound, which is KC8. But it just gives you a stoichiometric way to really measure out your electrons. So if you're trying to, again, reduce something, so you're not just trying to, again, check a whole piece of potassium in there. All right, so now let's kind of get back to the theory side of it and what we should focus on in our class. And so the first thing is to kind of understand how we learn to fill up electrons versus how they behave as metal complexes. And so kind of the difference is how we look at it. I thought I had it drawn out. And so basically, right, the electron configuration that we fill out just very, methodically, where we would expect it to be, for example, for titanium, 4s2, 3d2, right, since our D starts here, 3d. And this is for more of our titanium atom or whatever metal atom. But then really once it's as a complex, and again, we mentioned that our 4s and our 3d are really close in energy anyways, so it's just going to go ahead and act as a 3d4 ligand as it, 3d4 metal as it reacts with different ligands. And so generally, that's kind of why those numbers are written there, 3, 4, 5, 6, 7, 8, 9, 10, to kind of, again, tell you how it's behaving. And so often, right, nickel is referred to as D10, which again, right, doesn't match up with our previous filling up of the electrons. But again, now you can understand the distinction. So does that make sense, right? So this is in their metal state, and then this is as a complex. And so sometimes that's what they have you do in early inorganic chemistry classes is memorize, your transition metals, and then memorize what D groups they are. So D4, right, D5, 6, 7, 8, 9, 10. And then, of course, right, we kind of ignore our coinage metals just because they tend to act as usually 1+, and then these are usually 2+. But sometimes silver can do cool stuff. And so again, just kind of reappreciating our d orbitals. And so right now we have our 5d orbitals, so then we're going to kind of learn to fill in, well, how do our electrons then occupy our 5d orbitals? And so in our early approach too, and so this is also what it's saying here. This is the diagram I was looking for. So again, in our gas phase, just our free iron has this configuration versus our transition metals. So now it behaves differently. So this would be an iron 0. So the significances are both iron 0. So COs are neutral ligands, so they have 2 electrons to donate. So you can think back to CO's Lewis dot structure. So neutral. We could start to do some electron counting as well. And so this is, again, iron 0, so it's in the 0 oxidation state. It's not donating any electrons to these bonds. Again, CO is contributing 2 electrons. And then if you wanted to get our total electron count, and so now with metals, we generally have our 18 electron rule. So right, instead of the octet rule, it's now 18 electrons. Although that being said, they also like to follow the 17 and 16 electron rule along with other things. But we can see where we get our 18 electrons. So we have D8, so it brings 8 electrons to the party from iron. And then each COs, we have 1, 2, 3, 4, 5. Each one of them has 2 electrons. Oops. So 5 CO ligands, 2 electrons. So right, there's your 10. So 10 plus 8. So there's your 18 electron rule. And so then we can start to figure out, well, what does it mean then when we have iron 2 plus? So iron 2 plus, right, it lost 2 electrons. If we need to go back, oops, now I lost my P table. Ah. Sorry. Lost my periodic table. So right, we go back to our P table. Oh, iron is 8 neutrally if it's 0, and then of course 2 plus, lose 2 electrons, so now we're 3d6 there. And again, so not trying to get too into it, but we can at least start seeing how we got to our iron 2. So our chlorides are our X-type ligands, and so each one is a -1 charge. And then our nitrogens are neutral. So right, they have 1, 2, 3 electrons involved in bonding, and then they all have 2 to donate. So they're all donating 2 there. And then our chlorines are donating 1. So we could write out our total electron count for y'all. So iron, again, brings our 6 electrons. And actually, because this is confusing, so I'm going to count by the neutral method. So iron brings 8 neutrally. Each one of these, it brings 2. So 1, 2, 3, 4, 5, 6. So nitrogens 2 each. So 6. And then our chlorines bring 1 each. Again, that's how we got our oxidation state, so iron has to donate 1 to each one as well. So 2, so now we have 6 plus 2 is 8, and so this is actually 16 electrons. So pretty common, right, to have both 16 and 18 electrons. All right, let's see if we can practice that. And so we've gone back to neutral ligands to kind of help you guys. So see if you can figure out what we just did. So we need our oxidation state of our metal, and then our D count. So right, D6, D8, D10, whatever, and then see if you can figure out total electrons. And so for our purposes, we'll try to keep it easy with our electron counts, so things that we'll practice, so not all these crazy ligands. And at least one thing we could recognize is they're all octahedral complexes. So, right, metal, then they all have these 6 aqua ligands attached. So they're attached at our water, so donating 2 electrons to our metals. We could draw that out. Oops. I'll probably abbreviate, and I'm going to write it OH2, so we know that it's bonded right at the oxygen, so it looks kind of funny. So I'm just trying to draw my octahedral structure. So imagining our water ligands. All right, so let's go through them. What do we get for our oxidation state of vanadium? Bless you. All right, 3 plus. We know our waters are neutral. So what's vanadium? What? 3 plus, right? So 3 plus, and then what's its D count then if we're vanadium 3 plus? So look up vanadium. So what D count is it normally? So 5. So then if it's 3 plus, what is it? D2. Excellent. And then we can count up our total electrons. And so again, I would do that using our neutral method, but then we have to take into account our charge. And so we could add up, right, vanadium has 5 normally, and then 6 waters is 2 each, so we have 12, but then 3 plus, so we lost 3 electrons, so minus 3, and so we have 5, 17 minus 3, so 14 electrons there. Or you could have added, right, 2 plus 12, that would have also worked in that case. Questions about the first one? Is that relatively straightforward enough? So ask questions, right? Again, this could feel hodgepodgey. We're kind of trying to put things together, but it could feel all over the place. And so what do we get for our manganese compound? What's its oxidation state? So 3 plus again, and then what's our D count though for manganese? So it's 7 normally though, right? So then what's it as a 3 plus? So 4, so then D4. And then how many electrons do we have? So we could do 4 plus maybe 12 is an easier way to do that. So then how many total electrons? So 16, so following our 16 electron rule, I know, metal compounds don't, they do what they want. And then our cobalt to finish it up, so what's its oxidation state? So 3 plus again, and then what's its D count though? So D6 now in the 3 plus state. So just so everyone's on the same page, right, it's normally D9, so with our 9 there. And then total electron counts, we could do 6 plus 12, and so that gives us 18 for that compound. They could do the 19 electron rule.
Okay.
Yeah.
What about 20?
You know, you could probably find some 20s out there. I don't know about like 21, but yeah, your metals can be stretched to their limits. So that's again why people like to do research with them, because let's see what they can do. Let's oxidize them. Let's reduce them. So that. that is there. All right, other things that we should look at. So how they write stuff. So this also implies different things. And so we have, right, these sodiums, and I would call these, right, outer sphere. So basically, they're not connected to our iron, right? They're just kind of out, hanging out as a counter ion. And so sometimes you see this term as well, like in papers or something, if they're characterizing it, and they'll say whether it's inner sphere, so again, bound to the metal, or outer sphere, acting as a counter ion. So our sodium is just our counter ion here, right? It's not bonded to the metal, it's just acting to balance out this 4- charge. And so, right, what we can go through, it's actually bound to our metal. And that's what it's emphasizing here, is that we can dissolve it, it'll disassociate. These sodiums disassociate because they're outer sphere, but this is actually complex together. And so that's the compound with our -4 charge here, and then our cyanide ligands are negative, so you can remember that from your polyatomics. So these would be X type, but this starts to go a little bit beyond the course. So kind of, I want to introduce it, but then you would see this again in like an inorganic chemistry class where you'd go through this in much more detail than our kind of preview here. Let's see, other things we should say, and yeah, so then we can say, right, iron is in the 2+ oxidation state. Oh, they did label it for us here, but we could calculate that. So I said it was -1 X type, so -1 times 6, -6. So to get our -4, that had to be 2+. And then we've looked at some of these ligand substitution reactions. So we did the demo in class with kind of the silver. You saw it again with the 1-pot, although some questionable results there potentially. But you at least attempted to make these complexes. And again, right, we're appreciating, well, different ligands have different colors, but we still have to get into the why, so we're still kind of marching there slowly. But at least we're seeing, and this is a fun thing about metal chemistry too, and I mean, you either kind of know it works or if it went to poop by how your reaction goes. So what I mean by that is you should get a nice distinct color change, so like your compound goes. So in this case, right, it goes from green to colorless to blue-violet to colorless. So that's really nice. You know, I've seen transformations of like orange to green, or, you know, purple to green, that sort of thing. But if your reaction looks like mud or something, then it probably just made 1,000 horrible products, and, or intractable mixture is the official term. But yeah, so that's kind of the good thing. You know, if you add something and it makes a pretty color, a new pretty color, then that's a good sign for the most part. All right, so then, right, we want to at least kind of name our compounds. And so this would probably be on your exam, is being able to name kind of these sorts of ligands. So, right, we're not going to name anything crazy with some ligand that somebody made up, but just kind of these amine ligands or our aqua ligands. So let's look at how to name them. So again, these are our simple coordination compounds. And blah, 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 right? We mentioned that it's anything with our ligands attached. And then if we have a cation and an anion, then our cation is named first. And so looking at this one, so right, we have to kind of identify a few things. So they have our name written out for us. But let's just break down what we were given before we just jump to our name. So right, there's our counter ion here. Again, outer sphere. And so that's just kind of name at the end here. So our chloride, so name normally. And so to figure out our chloride, right, we need our oxidation state. And so that's where we get our nickel 2. So we can tell it's 2+ oxidation state, right, overall neutral. And then notice our prefixes. So we have hexa, and then we can name our aqua ligand. And so ligands are listed in front of the metal. They're bound to. And so we'll go back up to the example. And so here are all, right, the ligand names. So we've seen some of them before. So here it is again, right, fluoro, chloro, bromo, iodo. And then we have our cyano groups, hydroxo, so just our hydroxide acting as a ligand. Nitro, so anytime we add our nitro groups. Nitrido ligands, so those are common. Thiocyanado, so we could have named our iron thiocyanate compound like that. Isothiocyanado, so depending right where it binds, whether it binds at the sulfur or at the nitrogen, so it tells you. And carbonato, so this would be your carbonate ligand. And then oxo, and then these are our neutral ones, so our amine, and so notice the spelling on that, right, amine. Then aqua, carbonyl is pretty common, so we see a lot of carbonyl ligands, and then nitrosyl here, so a lot of NO, and this is also interesting for research. All right, so back to our examples then. And so now we can name this next one. So we have our copper hexamine bromide compound, and then of course, right, so ligands listed in front of metals, so when we go to write it, so hexa for 6, amine, then copper 2, again from our bromine here, so we had to balance out our bromide ligands. So copper 2 bromide. Again, just your anion at the end. If we have different ligands, then we list them alphabetically, so just like we did with our organic naming. So now if we look at this one, so right, this is our counter ion. So that's just at the end, okay, so that's our nitrate. Let's look at our ligands that are bound, right, so these are our ligands. And so aqua is first. So right, we only use the ligand names, so not the prefixes to alphabetize. So then it's penta for 5, so penta aqua. And then if there's just one, we don't need to say mono. So we just have penta aqua, chloro, cobalt, and then 3 nitrate. So notice, right, did you figure out it was cobalt 3, so we have, of course, our -2 from our nitrate, and then -1 from our chlorine as well, to give us 3+ overall. So there's our prefixes, di, tri, tetra, penta, hexa. And so then we have some different, so this is kind of confusing, so different naming systems. And so we have these prefixes, but then it says, what if we already have a prefix that denotes something? So this ethylene diamine here, so this ligand is named, right? So this is ethylene diamine itself. You can see its name, right? Diamine, to tell you. And so it's saying, well, we already have 2 amines, so we don't want to say diethylene diamine, or like, right, that's already strange. And so then we have these different prefixes, which is kind of confusing, but I think it starts to make sense again once you see it in practice. So if you had 2 of these, right, you would say bis ethylene diamine. So we're not di-di. Or this compound, this is a wonderful compound. And so this is palladium tetrachus triphenylphosphine, or tetrachus triphenylphosphine palladium. And so this is fun. So break down the name. It's in the formula, right? But you have tetrachus because you have 4 of these triphenylphosphine groups. I think I'll pull up a picture. I can spell it. Oh. And this is used a lot actually in, again, organometallic synthesis. It's a good starting material since it's a palladium 0 source. And it's a palladium 0 source that's not like palladium metal itself, right? So palladium metal doesn't really work, or any metal 0 source like this, just the metal itself doesn't generally work in these organometallic complexes. So having a metal 0 compound with ligands attached to it is a really good starting place. And so again, you can see, right, our triphenylphosphines, we have our phosphorus with 3 phenyl groups on there, so there's our triphenylphosphine, and then there are 4 of them, right? So this palladium has 4 surrounding it. This was a better, yeah, this is what I'm looking for, right? So it's really bulky, really sterically hindered, kind of cool, pretty crazy looking. I like phosphines. And then it's a really pretty structure, but it would be air sensitive. And then phosphine ligands are used a lot. I don't think, yeah, we don't talk about them in our class, but I might as well mention them since phosphines are used a lot. So these are all called phosphines. Triphenylphosphine, or you can use, right, tert-butylphosphine, isopropylphosphine. You can go crazy with the phosphines. But all right, do we feel okay on naming? Seems simple-ish. All right, let's take our 10-minute break. So I forgot to print out your homework, so I'm going to go print out your homework so you can grab that. And then we'll just finish up again looking at our ligands, and then we'll finally get into the isomers and our last bit, which is revealing the pretty colors. So hang tight. All right, I'll go print out stuff. Anybody else need anything printed? I have your quizzes up here if anybody was trying to sneak out, but otherwise I'll just hand them out at the end. I think I have, yeah, there's 1 lab, 2 lab copies. If I need to make more, I can. I think I have 2 printed, but we need more. All right, we'll be back in 10.
This is the quiz.
But I don't think so. Like, he had a backpack. Exactly. I'm like,
spectrum of things. I think that definitely could be, like, at least that's something that's on the students. Like, okay, if you have multiple units around, it's going to be releasing a bunch of hydrogen and nitrogen, which combined to versus a bunch of water, it'll be releasing oxygen. Which might make a difference. Yeah, I think it's been on the lower ones. Stuff. Well, I mean, if you get small enough, then just figure out small tubes of chemistry properly. Which is something that we learned in quantum physics from chemistry with different physics. Yeah, we were just like, yeah, quantum physics, that exists. That's pretty much mostly. Yeah, okay. Although we weren't technically told about the exclusion principle, but it's kind of something we gather from. There was. And it wasn't the gut thing, you hadn't talked about it. Dude, there were so many things in that quiz that he didn't talk about. It's like, oh yes, what is this? Dude, there were semiconductor questions, and it's like, you went over none of this. You said none of this. What do you mean? And so I had to go look it all up, and I wrote all the questions down. I swear. Yeah, right. Yeah, because otherwise I'd be like, well, I guess I'm randomly guessing that because I have no clue what this is. And then you went over like fermions and bosons and stuff, and we have not discussed that. Was it very end? This is fun, and we're at the end of the unit, so I don't really care. You guys don't have to learn anything more anymore. It's cool. I know chords are a thing, like, but I didn't really much look into them, so it's definitely just making the kids better. Yeah, I kind of know that. And then there's different like spin values. Yeah, I'm like that. I think, okay, yeah. Now we do one more step.
Congratulations are in order, and I looked at
What?
Yeah, I just haven't put it out.
Since I have to leave a little bit
Oh, yeah.
early.
Oh. All right, I'll put out the quiz if you want to grab it. Otherwise, I can hand it out later since it's a take home.
I was like, remember to record. Thank you.
Start having nightmares about it.
Don't worry, I got you back from now on.
Thank you. Just missing a quick lesson. Thank you.
You said the quiz was take home?
Yeah.
Yeah. Yeah, it's just, it's like right. That's so cool. It's just a street over. It's like right across.
Oh, no, I didn't know I needed more. Because I should have printed enough originally. Yeah. Oh, I have some more. Yeah, so yeah, take it home and then bring it back on Thursday, Tuesday. Oops. All right, might as well continue if everybody's back so we can try to get through everything. And so this is just saying that, right, you can have a ligand that can bind at two different places. And so the word that they use is chelating ligand, so that means it just binds at multiple points, or sometimes polydentate, again, right, binding at multiple points. And so you have this ox ligand here, oxalate, and so it would bind at both of these oxygens to your metal here. Same thing with this, the ethylene diamine ligand, so it's abbreviated EN. But again, right, it has 2 points that your metal could be bound to, so that's a nice stabilizing ligand there. And so more specifically, if we say something is bidentate, it means it has 2 points. So again, like this diamine ligand here. So that's often used a lot. Other than the diamine, right, I mentioned the phosphine. So this is another common ligand. So you have this phosphine pincer ligand with your metal here. And sometimes you can also have something that stabilizes your metal. So X could be, silicon, aluminum, germanium, so kind of those group 3 or group 4 main groups, gallium, etc. in there. And then, right, we have our phosphines, so the phosphines would then be the bidentate ligand. And then with that, we also have tridentate, and of course, this could probably go on and on as well. So I didn't put it up, but we could also mention that like crown ethers are used to sometimes stabilize metals. So crown ethers just have this sort of general form. And I didn't want to go into them too much just because there's a lot. But basically, right, they could stabilize something in that center as well, or maybe capture like a sodium ion. So it coordinates often to write different sodium, potassium. But sometimes you could get a metal in there as well. So, and there's a lot of crown ethers. So So you can, again, just kind of appreciate that there are crown ethers and they exist. All right, so now we'll get more into our theory again. So with our lecture notes, what we need to know. And so let's first start with our square planar complexes. So our square planar have two different conformations. So we can either have cis conformations, so we're the same ligands. So this would be if we have different substituted ligands, right? So if we have two on one side and the other two on the other, or they're on the same side, then that's called cis. If our same ligands are opposite one another, so our chlorine-chlorine here, that would be trans configuration. And again, you can usually tell by some sort of spectroscopic method, so looking for your stretching frequencies or something to tell you the difference. All right, so that's cis and trans, so that's for, again, square planar. And so now let's look at our other variations. And so now let's look at our octahedral complexes. And so if we have two different ligands here, so we have 2-chloro, right, 4-amine, and we're in an octahedral configuration. So if they are next to each other, right, so they're drawn like this, chlorine-chlorine, they obviously could be in like this orientation. So anytime they're next to one another, that's cis. Right, so our chlorine could have been here, here, so we could move it to different places. And so it's kind of easier to see it when it's trans. So if it's trans, right, then it's opposite from one another. And again, this would be pretty distinct because you'd probably be able to see a distinct stretching since both of these are bonded to our DZ squared orbitals. So that's something to kind of think about, or at least, you know, roughly is what orbitals do these kind of align with. And I mentioned the DZ squared since it's kind of obvious, right? It's our one on our Z axis. So it's up and down, so we have something trans there that's bonding along our DZ squared. And so notice, right, we have difference in colors, so that would give us a good, again, distinction between the two. And so we could use our spectroscopy, right, and we could measure our absorbance then at different wavelengths, and this could give us, right, how much we have of our cis and how much of our trans conformation as well. So different methods, unless they're different by NMR, so that's also another technique, right? So there's different techniques to characterize them. And so now we have our other variations. So now if we have 3 and 3, they can be in different conformations. And so your book uses this term that I'm unfamiliar with. So they call it cis-cis, and you can kind of see how they're all cis to one another, right? Nobody is a cross. But I kind of see it on the same side, and usually how it's explained, because you have, I'm used to the term back, like facial, like it's on the same facial side. And you can kind of think about drawing a plane with all of them, and we could orient our octahedral complex. They'd all be sitting on the bottom on the same face. So that's, I'm used to the term back. So I have not heard of cis-cis. So on an exam, I'll take both, but just be aware, probably if you look in the literature, you'll see that fact term or other sources. And then we have what your book calls cis-trans, and you can see kind of what they mean, right? We have, obviously, they're trans, and then that leaves that third one as cis relative to both of those. But again, the term that you'll probably see is the mer isomer, and now they're kind of in the middle, so a little odd. So just be aware of all those terms. And so now this one, right, you can't rotate it to be on the same face, so they're always and they're trans. So. And this is, again, just kind of more awareness and probably what we'll cover in class. But we can also have different isomers in the sense of linkage isomers they're called, so basically how they are attached to the metal. And this can also happen, as it undergoes different oxidation states potentially. But we can see here it's bound to our nitrogen, and then in this conformation it's bound to our oxygen. So just little differences there, so that can happen. And then our optical isomers are just defined as our non-superimposable mirror images. And so now we see we have, right, 3 different ligands, and the point is, right, we can't rotate them so where they are matching. So, and I think you probably did this in lab, but we could go over this again if we needed to, maybe after class with some models of just kind of working through that. And what kind of helps is they do show the mirror here, so that's a good way to draw it. If you're ever trying to draw it on the exam, make yourself a mental mirror plate, and then just start mirroring everything. And then you see, right, by rotation, though, so if you try to rotate it, it would not be the same. So, right, this is rotated, they're not the same, so that's a key point. So mirror images, not superimposable. All right, so let's get into probably the important part, is our crystal field theory. And so again, we're just taking kind of a simplified approach here. And so what we need to understand is, well, right, our d orbitals are not actually degenerate, right? So we kind of learned that, they're degenerate, so meaning they're the same energy level. So I'll use that term. So here they're degenerate, but this would again be more for its gaseous metal ion state. And so the thing is, well, what happens when it actually gets into a compound? And so we won't get all too into it because it starts to again get complicated. But what we need to understand is that these are our octahedral splitting energy. And well, what does that mean? So this means that this is the energy levels of our ligands in the octahedral configuration. And well, let's kind of break this down again so we can appreciate kind of what's going on. And so down here is going to be more of our non-bonding. And then what is up here is kind of more of our anti-bonding from our bonding. And so what I want you to notice is these are the orbitals that are participating in bonding. And so we can kind of see this. So if we go back, and let's just first draw out, right? Again, we said this was for octahedral. So this is basically who's bonding with this structure. And so again, we won't get into the math, but basically what this comes into is these irreducible representations. What we can do is, okay, well, let's look at our D ligands again, if I can find them. Okay, we're looking at our D orbitals. And so the ones that kind of match, again, pictorially with our octahedral complexes would be these two, right? So we can see that. So it would bond on our z-axis here. So we see that, right? Bonding with our dz squared. And then the rest of our 4 octahedrals, right, lie on our xy plane. So they are bonding with our dx squared minus y squared. What's kind of confusing is we're actually kind of looking at the anti-bonding orbitals on this side, right? So they're making bonding orbitals down here with our ligands, but we're not looking at those right now. So these are kind of the corresponding antibonding of our metals. And so I at least want you to appreciate that there are other configurations. We'll bring up tetrahedral just because it's the opposite of octahedral, which is kind of funny. Or maybe I only think that's funny. So tetrahedral starts off as 5 degenerate ligands, and then it's flipped now. So X, Y, Y, Z, X, Z, and then our non-bonding ones were the ones that we said were bonding in our octahedral. So X squared minus Y squared. And again, I think for our purposes, we'll mainly just focus on octahedral complexes. I was trying to show, no, I'll look for another article for reference. So let's keep moving. And so the next thing is, well, how do we relate, again, what's going on here? So we have this splitting energy. And well, now we can start to get into how we can quantify this and understand what's happening. And so going back, if we think way back to first quarter of chemistry, so right, we said, well, we can relate our energy. So thinking back to our energy levels, right, well, we said, well, our energy is related to our Planck's constant times our wavelength. So then we can figure out, right, our energy from there. And so then our differences in energy, so we'd be looking at this transition, and then of course, right now we can add numbers to this. And so same sort of thing, right, we're just appreciating the transitions just like we did before, way back when, but now we're just looking and focusing at those d orbital transitions. And so kind of, right, the next piece to that, again, going back to, well, why are there pretty colors? It's because it just so happens that most of these transitions occur in the visible region. So most transitions, at least, right, for a lot of these metal complexes. So that's why we get the pretty colors, right? That's why we can see it. And again, that's why we'll be able to quantify it. And so it just goes back to, right, the organic compounds just have their transitions in the UV region, so they all look white, while all these are not. And let's add into there, which is equal to Planck's constant times our speed of light over our wavelength. So that might be more helpful, since we usually, right, refer to wavelengths since we like the pretty colors. So now let's look at this. And now we can, again, look at these different absorption spectrums like we've done before with pretty colors, right? You see where it absorbs. And so then we can see the absorption in our kind of blue region. So it excites our d electron from our T2G to our EG set. And so, right, we have a red-purple complex, so it kind of absorbs in the opposite. Other things to appreciate. So titanium, right, so then this is titanium 3+, D1, and so this one is a little bit simpler to understand since, right, we only have one electron in that system there as well. And let's see, let's ask a question then. So what do we do with this? And so let's see how we would apply this, right? So we have our graph here, and then we would try to say where our maximum absorbance is. And so for our purposes, let's just say this is about 480 nanometers. And so now we can actually ask that question. So what is the octahedral field splitting energy. So see if you can solve that. And I'll rewrite our formula since we probably forgot it from first quarter. I mean, admittedly, I forget this formula. And do we remember Planck's constant? I'll put it up. So 6.626 times 10 to the negative 34. I think that's joules meters per second.
That's a 240
What?
No, just physics things.
Oh.
Instead of using, for this formula, we just use Hc equals 1,240 electron volts.
Oh,
This is a
gotcha.
fancy number.
Well, if you give it to me in electron volts, you know, I'll have to translate it back to joules.
Not very useful, right?
So then we can plug in our values. So 6.626 times 10 to the negative 34. So we're in joules based off of this. If you're in another unit, again, just label your units accordingly. And then I'm going to take the lazy conversion, so 480 times 10 to the negative 9 to get that nanometers to meters. And then what did people get for this one?
I got, at least whenever I use the electron volts and convert it into joules, I got 4.14 times 10 to the negative 19 joules, and then I did the second one using the Planck's constant to like just do it that way, and I got 4.14 times 10 to the negative 19 joules.
That sounds excellent. So yes, I get that as well. So fancy if you wanted to do it in electron volts. If you really wanted to leave it on an electron volts on the exam, again, I wouldn't fault you. Just make sure you label your units so I know what the heck you're doing. Excellent. Any questions about this thing? All right, so now we're saying, okay, right, we can measure our transition. We can correspond, right, our lights. We can figure out our energy of our octahedral splitting here. And so now let's go back to that other term we had mentioned. So we mentioned this low spin versus high spin complexes. And what does that mean? So first of all, let's kind of look at, well, what the heck do those terms mean? So low spin means that we fill in our lower energy levels first. So we have our low spin, and so that's kind of what's implied here. And so let's see, so they have, right, both of these are D6s. So we have 1, 2, 3, 4, 5, 6. And so they filled in all on the bottom first on our low spin. And then high spin is when we fill up all D levels before pairing. And so now we're kind of getting into it slowly, so we're still kind of building into this and trying to understand it. But basically there's our overall consideration. So basically we're saying, is it more favorable to fill them up in low spin such that, right, we're pairing them? So obviously, right, these have to be paired. And don't forget that, right, we do kind of pay an energy price. So pay energy price for pairing. And then it's kind of implied here, but it's saying, or is it more energetically favorable? So maybe this octahedral splitting energy is smaller. And it's actually more favorable to not pair them first, but rather, right, pay the energy price of going to these higher energy levels first, and then you go back and pair. So kind of which is more energy intensive, right? Does it cost more energy to put it into our higher orbital, or does it cost more energy to pair? So that's what kind of dictates. And so let's kind of look at it, because it isn't always intuitive, right? So that's kind of what I mentioned too with the research, is we don't always know. So we'll go through general trends, but then that's where we need our spectroscopic techniques. And so right now we'll point out kind of the difference. So right, this, and remember this term, so it has all paired electrons. Do you remember what that's called? I think we've covered it. Diamagnetic. So diamagnetic. So most compounds normally are diamagnetic, which just means they show up kind of normally as sharp peaks on an NMR. But then if you have these unpaired electrons, and this is where, right, the whole spin state comes into play. So now our unpaired electrons, now this would be paramagnetic. And basically it makes your NMR spectrum look blobby and like all spread out. It would cover a much larger range than would be considered the normal range. And it would again look like blobs. So your diamagnetic kind of looks like all these sharp peaks. And then paramagnetic is kind of more blobs and weird. But I'd have to show NMRs for it to kind of make more sense. All right, so then now we're comparing these. And so now this is comparing our two different compounds and kind of asking, well, why is this? And so let's look at our scenario. And so we have our iron cyano complex here. And so it says it's low spin diamagnetic, so that's helpful. And kind of the implication is, right, so this splitting here is much larger, right, than our kind of pairing energy. So it's much more favorable to pair them as opposed to try to promote them to our higher energy levels. If you compare that to our fluorine though, so fluorine, right, so same thing, so kind of compare them. So they're both octahedral. So no difference there. And then we can even compare, so they're both, right, iron 2+, so Fe2+, so they're the same. So that means they're both D6, right, D6. So again, the only question is how do they fill? So how do those 6 electrons fill up on this structure here? And so again, right, we're only looking at a very small sample too of kind of our MO diagram. So we're only looking at the metal part and kind of how those D ligands fill in. And so this is again, right, what it's telling us. So basically the octahedral splitting energy then is less than the pairing energy. So in the fluorine case, it was more favorable to promote those electrons. And well, again, how do you know this? Well, they have this spectrochemical series. And again, this is just kind of a guide, right? So this kind of helps us, but like we saw with those papers is, you know, we have to verify it with NMR. So then the question is, okay, if we predict it to be high spin, you know, then does it match spectroscopically? And so now this kind of tells us what we, again, kind of expect them to be. So iodine, bromine, chlorine, fluorine, these all tend to have a low octahedral splitting energy. So they tend to be high spin versus if we get down to like CO ligands or RCN like we saw. So these have a much higher energy, octahedral splitting energy, so they tend to be low spin. And so I think that's covered a lot on your homework. So it kind of goes through, you know, how many unpaired electrons, diamagnetic, paramagnetic. And so you just have to go through, write what we expect. And so that's something, you know, on the exam that I'd want to put is like, what would you expect? You know, paramagnetic, diamagnetic. So being able to identify that. Yeah. We can talk about why that is a little bit. So let's get into kind of the why this is, because that's somewhat interesting. But again, you'll probably cover it later. But it's good to get a sample. And so again, it mentions that these tend to have a low octahedral splitting. And so, right, we can think of fluorine. So fluorine is a sigma donor. So that's kind of more simple. Now, if we compare that to our carbonyl ligand, and this is why we have a higher octahedral splitting, is so CO especially can do what's called pi back bonding. And so let's think about this for a second. So, right, we have our CO. And so now we have to start thinking back to its Lewis dot structure. And so we have, right, our different pi bonds. So we have, right, it's donating its 2 electrons. But then it also has, right, these P, so we'll call them, right, PX, PY ligands. And so they're kind of oriented. And so again, let's think about this. So now let's kind of redraw this. So we have our metal, and we're ignoring this, right? So this is bonding with our DZ squared normally. But then let's think about what else it can interact with. So again, our carbonyl is coming on here, and let's just focus on our PX for a second. And so remember, right, the shading of our dumbbells. And then think about what the metal has, right? So then the metal has these d orbitals. And so it just so happens that these d orbitals are in the right orientation. And so, again, not only do you have that sigma bond, but then now they're able to do, again, that additional pi back bonding. And so because it can do this pi back bonding, that not only makes it a really strong ligand, but then what that does to our antibonding is it throws it up even higher in energy. So then this gets even higher with our octahedral splitting diagram. And so that's why we tend to have a large splitting there. And so again, right, that goes back into our behavior. How do they act, right? Why do the different ligands produce different colors? So it all depends how strongly they're donating, right? And again, CO is our most extreme example where we actually have pi back bonding, so that's a cool phenomenon that CO can do, but right, fluorine's not going to do the same. So they act differently, then they give different splitting energies. And then obviously it gets more complicated from there. So I think that's pretty much it. I think we ended a little early, so we could look at your homework. I was trying to show you kind of more previews, but I don't know why I can't find the right diagrams that I'm looking for. Here we go. This is what I was looking for. So this is from Wikipedia. So it has a crystal field theory. And so it's kind of nice, actually, their Wikipedia article. But what I wanted to show you was at least the energy diagrams. So again, for our purposes, we're mainly just going to look at the octahedral energy diagram. But just for your future knowledge, right, all the different geometries have different energy level splitting diagrams, again, depending, right, what they're aligned with. So you can, again, just appreciate it, take it in. So square planar is kind of cool. This is, you know, one you would look at probably in an inorganic chemistry class. Again, right, just appreciate it. So that's the different orbitals, rearrange their energies depending on our geometry. So there's our tetrahedral again that, you know, be somewhat familiar with, but mainly octahedral. So at least you know where this is, where you can find it, you know, if you need to reference that again. All right, what should we do for the last kind of 10 minutes? Oh, which number you want to do? Is that just the first one, the cobalt? All right, let's do that one. I'll just write it out instead of printing it. So let's go through it. So let's just start off. So it has our cobalt cyano complex 3 minus, and then it asks us, right, how many unpaired electrons. We have to figure out high spin, low spin, draw it out, paramagnetic, diamagnetic. So kind of start it, and then we'll go over it. So what do you think? How would we approach this, right? Go back to your notes here. Where is cyanide typically on our trend? And then how does that match with the decount? So I'll go back. So take your time to look at it before we reveal everything. And so based Well, I guess first of all, right, we could start off with octahedral complex, of course, right, because there's 6 things, so we can at least start by drawing this out, just our octahedral framework. And then, well, they use a term, so let's go back to our notes. And so this is going to be, right, our strong field ligands over here. So we should have added that to our notes. So kind of strong field, just implying, again, that they make a large difference. And so that means that they're going to be low spin, typically. And so these would be weak field. And so based off of our ligand here, so do we expect it to be low spin or high spin then? So low spin, right? So again, our cyanide, strong field. And I just like to write, large splitting gap. Okay, so that means that we need to fill the bottom first. And then what's our D count here? Or what's the oxidation state of cobalt? So did you say D6? Yeah, so D6, right, 3 plus, since we have our cyanide, so they're all -1, so -1 times 6, -6. So our cobalt has to be 3 plus, so D6. So with our strong field ligand, again, just based off of this, right, because we have no other evidence, so they didn't give us any spectroscopic evidence of anything. And so now we just fill it up where we're pairing on the bottom. So I probably should have done 1, 2, 3, 4, 5, 6 before pairing. And then, so then we can answer, right, 0 unpaired electrons. And so the clue, of course, right, again, if we were making this compound and then trying to figure out were we correct, well, then we'd want to take an NMR and determine that it's diamagnetic. Right, so diamagnetic, again, it has all paired electrons, so it would come up with a nice sharp spectrum. Actually, the only difficulty in this one would actually be obtaining a spectrum. So there's no protons, so you'd have to do a 13 carbon NMR or maybe 15 nitrogen, but I'm not sure how difficult a nitrogen NMR is. Do we want to do the next one, just so we're okay? So go ahead and look at number 2, so that cobalt F6 3- compound. And so what do we think about that? So what's our D count or oxidation state? So still 6, still cobalt 3 plus, so that's a good comparison. Except, so what's the difference now? So is our fluorine, so now we think it's going to be high spin from, again, right, this is a weak field. So small octahedral splitting. So yes, we would expect it to be high spin. So 1, 2, 3, 4, 5, 6 now. And so how many unpaired electrons? What'd you say? So 4. So 4 unpaired electrons, and then of course it would be paramagnetic since we have any unpaired electrons. So does that feel okay? And I think the rest of your homework should be pretty straightforward, so just kind of comparing with the different D counts. And again, right, we're mainly focusing on octahedral, so I just looked. So there is some tetrahedral on the back, but at least the lines of your d orbitals are kind of filled out, right? Same concept, weak field, strong field. Just use that to dictate. All right, we'll end there, and then of course, if you have questions over the homework, I'm happy to chat. And again, just try to take most of it in as fun facts, and then we can focus on the homework as to like what we're actually going to be kind of tested on. But just trying to at least expose you to all the wonders of chemistry that awaits.